Last week, the machine earned a token, the right to post as you and as your company page. This week, we keep that right alive because the token you just stored has a countdown on it, about 60 days, and then it's a string of garbage. And the machine is supposed to run for months without you ever logging back in. So we build the token store, the part that keeps the whole system connected while you sleep. Here's where we are. The data layer is lit, OAuth is wired. And the box we flickered at the end of last week, the token store, ignites today. By the end of this video, that box will keep itself alive. It stores when each token dies, and a scheduler refreshes every token before it does. That cyan path, OAuth, into the token store, into the scheduler, is the loop that runs on a clock while nobody's watching. Let's open the box. Start with the way this usually dies, quietly. The standard advice for expiring tokens is make your call, catch the 401, refresh the token, retry the call. And for 60-minute tokens with steady traffic, that's fine. Something hits the API every few minutes, so the refresh fires long before anyone notices. Now, stretch the token to 60 days. Your app might not touch that integration for a week or 3. Nothing triggers the refresh because nothing failed yet. The token slides past its expiry in total silence. And then the scheduler finally wakes up to post, and the very first call comes back 401, with no valid token to retry with. The first failure isn't a hiccup you recover from. It's an outage your user discovers before you do. Reacting to failure only works if you fail often. At this time scale, you have to act before the failure. So the first move is to write down the clock. When you exchanged the code last week, the response carried expires in a number of seconds, 60 days worth. And here's the trap. Expires in is relative to the instant the platform sent it. Store that raw number and it's a lie by the time it hits the database, because now has already moved. So convert it once at write time. Take the current time, add expires in seconds, and save the result as an absolute timestamp. Expires at. Store that in the token row right next to the access token and the refresh token. That one column changes everything downstream. The machine no longer has to fail to discover a dead token. It can look at the row and see, in plain terms, this one dies September 6th at 2:20. A scheduled job can now ask a simple question in Squill. Which tokens expire in the next few days? Store the token, and store the clock beside it. Now be precise about what you're actually storing, because it's two different things with two very different lifetimes, and people conflate them constantly. The access token is the one you attach to every API call. It's deliberately short-lived. Think of it as a shift badge that expires, so that a stolen one is worthless in a day or two. The refresh token is the other thing entirely. It's long-lived, you use it rarely, and its only job is to mint fresh access tokens without dragging the user back through a login screen. It's the keycard, not the badge. That asymmetry drives every decision from here. Because the access token is disposable, you can be relaxed about it. If it dies, you refresh. But the refresh token is the credential that has to survive for months unattended. Lose it and there is no recovery inside the system. The only fix is the user reauthorizing from scratch. So everything valuable we do next, encrypting at rest, rotation, careful failure handling, is really about protecting that one long-lived secret. So how does a refresh actually work? It's the same backchannel exchange you already built for the Connect flow, just without the browser this time, because there's no human to ask. Your server makes a server-to-server post to the platform's token endpoint. The body says grant type equals refresh token, and it carries the refresh token you stored, plus the same client secret that never leaves your server. The platform validates all three and hands back a fresh response. A new access token, a new expires in, so you recompute expires at exactly the way you did at write time, and, crucially, on many platforms, a brand new refresh token. If it sends one, the old refresh token is now dead, and you must overwrite it. Miss that detail, and your next refresh will present a token the platform already retired, and it'll be rejected. So the whole operation is, post the grant, take back the new access token and clock, and if a new refresh token came along, swap it in atomically. One quiet HTTP call, and the 60-day clock resets to full. This is the heart of the episode. Instead of waiting for a call to fail, you run a scheduled job, a cron, on a fixed cadence, say once a day. Every time it wakes, it asks the database one question. Which tokens have an expires at inside my window? Anything dying in, say, the next 7 days? For each one, it runs the refresh grant we just built. Two things make this robust. First, the window is not the deadline. It's slack. By refreshing 7 days early, you get 7 daily attempts before the token actually dies. If the platform is down today, you try again tomorrow, and you've still got 5 days of runway. A single failed refresh is a non-event, not a crisis. Second, jitter. If 1,000 tokens all expire the same afternoon because you onboarded a cohort together, a naive job refreshes them in a tight burst, and you hammer the platform, maybe trip a rate limit, and fail the whole batch. So you spread the refreshes across the window with a little randomness. Same guarantee, none of the stampede. Proactive, windowed, and jittered. The token gets renewed on a calm schedule, days before anyone would ever have noticed it was close. Rotation deserves its own minute because it's where a security feature can quietly bite you. Many providers rotate the refresh token on every use. You refresh, and along with the new access token, you get a new refresh token, and the one you just spent is now permanently dead. Why do that? Because it turns a leaked refresh token into a self-detecting problem. Imagine an attacker copies your refresh token. Now 2 parties hold it, you and them. Whoever refreshes first gets the new pair. The other one, when they try, presents a token that's already been retired. The platform sees a refresh token being reused after rotation, and a well-designed provider treats that as proof of compromise. It revokes the entire token family on the spot. That's great for security, and it means 2 things for you. 1. Always persist the newest refresh token immediately, overwriting the old. A stale copy in your database is indistinguishable from a thief. 2. Never let 2 of your own jobs refresh the same token at once, or you'll trigger the reuse alarm on yourself and lock yourself out. Rotation is a gift, as long as you're disciplined about only ever holding the latest key. Before we handle failure, handle theft, because we've now concentrated something dangerous. Every long-lived refresh token in that table is a durable key to a real person's social account. That table is, pound for pound, the most valuable thing in your database. So don't store the tokens in plain text, where a single leaked backup, an overbroad select, or a compromised read replica hands an attacker a pile of live credentials. Encrypt the token columns at rest. The clean way is envelope encryption. You encrypt each token with a data key, and that data key is itself protected by a master key held in a key management service, a KMS, that the database never sees. The practical payoff is separation. Your database holds ciphertext, the KMS holds the key to decrypt it, and an attacker needs both. A stolen database dump becomes a wall of unreadable bytes instead of a working set of keys. It's a modest amount of plumbing, and it's the difference between a bad day and a breach notification. Finally, the part everyone skips. What happens when the refresh itself fails? There are 2 kinds of failure, and conflating them is the bug. Transient failures, the platform timed out, a 500, a network blip, those you retry, and the window we built already gives you days of runway to do it. Terminal failures are different. If the platform says invalid grant, retrying is pointless. The refresh token is genuinely, permanently gone. The user revoked your app, or changed their password, or rotation caught a reuse and killed the chain. When that happens, do 3 things. Mark the token dead in the database, a status like needs reauth, so no job keeps hammering a hopeless refresh. Stop trying, and route the operator to reauthorize. One quiet email that says, reconnect this account, sent long before any real posting deadline, because the window bought you that lead time. That's a calm maintenance email, not a 3 a.m. outage. One more piece of hygiene. Wrap the whole refresh in a single flight lock. If your cron and a live request both notice the same token is expiring and both refresh it at once, you'll spend the refresh token twice. And on a rotating provider, the second attempt looks exactly like the reuse attack we just talked about, and the platform revokes you. So take a lock per token. 1 refresh in flight at a time, everyone else waits for the result. Proactive, windowed, encrypted, single flight, and gracefully degrading. That's a token store that keeps the whole machine connected for months without you. So step back and look at the token store, lit. You store expires at, not just the token, so the row knows when it dies. You keep the 2 credentials straight, a disposable access token, a precious refresh token, and you guard the refresh token with encryption at rest. A scheduler refreshes proactively, inside a window, with jitter, days before expiry, never on a 401. Rotation is handled by always holding the newest token, and when a refresh fails for good, you mark it dead, single flight the retries, and send 1 quiet email instead of causing an outage. 1 background job and a clock, traded for months of uptime nobody has to babysit. The machine now stays connected on its own, but everything it's storing lives in 1 database, and right now, any query can read any row. Next week, locking that down at the database itself, with row-level security. See you Wednesday.